It's my great pleasure to welcome all of you today to today's online seminar on interval methods in control engineering. And it's my pleasure to welcome today Lorenz Gillner from the University of Applied Sciences in Wismar in Germany. And Lorenz, he received his PhD, his Bachelor of Science degree, firstly in computer science and multimedia engineering in 2020. From this University of Applied Sciences in Wismar in 2020, then his master, 22, his Master of Science degree. And since then, he has been working as a scientific researcher towards his PhD thesis, which is co-supervised by Katja Auer, who is here in the audience, and by myself. And we're now looking forward to your presentation on interval methods for the GPU in global optimization. Lorenz, the floor is yours.
Well, thank you very much for your introduction. Yes, as already mentioned, this is part of my PhD project, which I'm currently working on. And in this project, we are asking the question, how can we use interval methods on graphics processing units? And this is a question which is becoming, from our point of view, very important, because if we take a look at the top 5 of the top 500 supercomputers in the world, we can see that almost all of them are not CPU clusters anymore, but heterogeneous systems using some accelerator hardware, specifically modern GPUs. And in this context, we are asking the questions, what are our possibilities to use interval methods on such accelerator hardware? And this is going to be the overarching topic of my talk today. This is the outline of my talk. And first, before we dive into the world of GPUs, let's talk about interval libraries on the CPU, because there are a lot of interval libraries for the CPU. And as we can see, a clear favorite for interval computations is, of course, C++, probably due to its close to hardware control mechanisms. But we also have some wrapper libraries, for example, some high-level PyIbex for the Python, which wraps the Ibex library. And yes, so pretty much every major programming language today has interval arithmetic available. And most of these libraries offer an intuitive way of programming, thanks to operator overloading and object-oriented programming, which allows the programmer to focus actually on writing describing their problem rather than focusing on how to write intervals and so on. But this is nothing new. Interval software has been around for quite some years now, and they are quite extensible. Let's talk about, for example, FATBAT, which is an automatic differentiation library, which was designed with interval arithmetic in mind, which is quite nice. And there are many, many toolboxes for special use cases. For example, verified solvers, optimizers using uncertainty, or special visualization toolboxes for interval methods. But nowadays, now that multi-core processors are basically the de facto standard for modern workstations, we should ask, what about parallelization? And in fact, the library CXSC is one of the most documented in that regard, because it is considered thread safe and it has been tested in multi-threaded environments or distributed environments using MPI or OpenMPI. But many traditional optimization algorithms with intervals were designed at a time where single core CPUs were the norm. So many branch and bound type algorithms are not actually designed for parallelization. And this will become more important later. And another topic which hasn't been an issue for the past 10 years or so, because most workstations nowadays use an x86 or AMD 64 processor, is portability. Now we see a trend in the industry that ARM CPUs are coming back. or special special hardware for special tasks. So interval libraries for the CPU are not really portable because they often depend on specific header files, which are system specific, or built on rounding libraries like MPFR or CRLibM, which are again specific to a certain hardware or inline assembly, which makes it not very portable at all. And that's where the question of interval methods for the GPU comes in. How can we use this broad, already existing plethora of interval tools on the GPU? Can we even do it? So let's talk about GPUs. And we will start with a short introduction on the GPU. For those of you who are not familiar with GPU computing, the GPU was originally designed for computer graphics. It's a co-processor that's specialized for, or originally specialized for raster images or 3D computer graphics. And nowadays they have become so powerful with very high clock rates and large amounts of video RAM that they are not used in computer graphics exclusively, which is why we talk about general purpose GPUs. So they are used in very broad areas of research. And the core principle is the SEMT, not to be confused with SEMD. SEMT means many low performance cores can solve the same task in parallel, which optimally should be very lightweight. And but it should be noted that most GPU libraries work with an abstraction layer of so-called threads, blocks, and grids, which are not the physical cores on the multiprocessor, but a concept. So a GPU with only let's say 500 cores can still solve a problem involving thousands of threads because it can handle this abstraction layer. And in my work, I'm focusing on the NVIDIA manufactured devices using the CUDA architecture because of their very high market share. So let's look again at the top 500 supercomputers. And we can see, although there are many different NVIDIA's co-processors listed here, they are pretty much all the same actually. So yeah, only a fraction of high performance computers use AMD graphics cards, but that might change in the near future. And in this figure right here, we can see the fundamental differences between a traditional CPU and the GPU. On the CPU, we have large caches and a high bandwidth interface to the DRAM, while on the GPU, we have only very, very small caches, which is why we have to be careful when doing memory intensive tasks, because otherwise we might run into some memory problems. And another problem on the GPU is that access to the DRAM is very expensive and might slow down computations. So just something to keep in mind when working on the GPU. And what about GPU programming, now that we know the foundations of the hardware? The main obstacle of GPU programming is that every vendor has their own library. So unlike desktop processors where everybody basically has the same foundations, we have on the GPU for every vendor a specific language model we have to learn, although CUDA and ROCm, which is the AMD equivalent, are pretty much interchangeable. But then again, there's many different ways to program different GPUs. And one goal in the past has been to find a common ground for all GPU manufacturers to support a single language, which was OpenCL. Unfortunately, this standard is no longer supported on all devices, so that has been a major setback in my opinion. And yes, when it comes to programming the GPU, we typically use something called kernel programming, which is very similar to vectorized programming. Some of the audience might be familiar with vector programming from MATLAB or languages like R. where we basically define a function and then execute this function in parallel to a large data array. And this splitting is handled by the GPU automatically. And one aspect of the GPU is, which is interesting for interval methods specifically, is the rounding control. Again, I will focus on CUDA devices for here, but CUDA devices support directed rounding for all arithmetic operations, which is stateless as opposed to the CPU, where we have to change the rounding mode every time we want to round a different direction. So traditionally, we would program a GPU in something like C or C++. However, this requires a lot of boilerplate code, memory allocation, memory deallocation, and so on. So there has been a shift in programming language development, or a general industry trend of writing high-level GPU programs by taking a very simple language like Python, for example, and extending it with some GPU functionality. One example is Number, which introduces a just-in-time compiler for the CUDA device. However, it has been shown that just-in-time compiled CUDA code will never be as fast as actual ahead-of-time compiled CUDA code with C or C++, which is why they are developing some alternatives, namely Codon or Mojo, which are both ahead-of-time compiled Python-compatible programming languages with the GPU support. But again, they are still under development, so we might have to fall back to C++ for the moment. And what is the current state of intervals in CUDA? Well, there is actually a basic interval arithmetic library. It was originally included in the CUDA toolkit back in 2013. Unfortunately, this interval library is very incomplete. It is not well tested, and it has been removed from most up-to-date CUDA versions. When we are working with intervals, we also want to do automatic differentiation in many cases, which is possible on the GPU with a library, for example, called CLAD. Unfortunately, this library can only handle native data types and not intervals. The same goes for example, solving initial value problems on the GPU, which is possible, but not with intervals. And so the current interval library landscape for the GPU looks very much like that here on the right. There is only one public CUDA library, and there have been implementations for OpenCL. However, they are not public to my knowledge. So we are stuck with a single library for the GPU at the moment. But also in the context of this seminar, we have had a presentation about Julia and GPU programming, and I think Julia is very important in this regard because it is a high-level language, a very high-level language, and it makes it very easy to write GPU programs. So, for example, here on the left, we see a simple Julia program that applies a function in a vectorized way to a large data array. And if you want to execute this code on the GPU, we simply have to wrap our data array in a special data type. And everything else happens automatically. So the developers behind the CUDA backend, again, for different devices, one would have to use different backends. But the automatic code generation for GPU devices is working very well at the moment, mainly due to the fact that the CUDA compiler is actually based on the same technology as Julia itself. So this language allows us to eliminate this hardware barrier by writing very generic code. And there is an interval library for Julia. However, we can only use intervals on the GPU in the Julia language with some limitations, because rounding, again, is very CPU specific. The GPU supports next float and previous float methods, which allows us to do at least some rounding control on the GPU with generated code. But trigonometric functions, for example, are not very usable at the moment. So something to keep in mind when working with Julia and intervals on the GPU. So let's look at some experiments we did with GPU programming and intervals, and we looked at Julia and C++ in that regard. And our scenario is a parameter optimization, a parameter estimation scenario. So given this classic two-compartment model, which is known from the literature, with given initial conditions and we want to estimate the parameters of this model, and the parameters are known to be contained in this search space. And for the first step, we also have the analytical solutions to this problem, which is not optimal, but it should reduce the dependency effect quite a bit in this way. So when we want to estimate our parameters, and if we have some measurement data given for our system that we want to that we have the model for, we can use this objective function and minimize it with regard to our parameter box P. And in our experiments, our goal was to minimize, to reduce a possibly very large search space. And we do the following. We have the initial search space. We bisect this search space into smaller subboxes of a predefined width until every box is lower than or equal this predefined width and make up our whole entire search space. Then we apply the monotonicity test to every box in every subbox in our search space, meaning that we only keep a box if the gradient of our cost function actually contains 0. And then we hopefully reduce our search space to a smaller one by building the convex hull of all suitable boxes and maybe reiterate or run a different optimization problem algorithm on this smaller box P star. So that this is only for illustrative purposes. From a bigger cube, we get some, smaller cubes or smaller boxes that we can later work on. For our experiments, we had 16 measurement points for the y2 dimension only. So we can reduce our cost function to this expression, only concerning y2. And as already mentioned, we used CUDA C++ and Julia for a comparison of both. And we use an extended version of the CUDA interval library. In 2013, 2 students from Denmark actually extended the original library, and we again extended this library and used that for our experiments. And because initially there was, as I mentioned earlier, no automatic differentiation available on the GPU for intervals, we used manual differentiation for the computation of the gradient, and later developed or ported parts of the FATBOT library to the GPU, so that we now have a very rudimentary library for automatic differentiation with intervals on the GPU. And we ran our test on a NVIDIA Quadro RTX 6000 with little over 4,000 compute cores. And what if we don't have the exact solution available? We can try to approximate the actual solution by using Euler's method. So taking our cost function and substituting, in our case, the exact solution for y2 with the Euler approximation, we get the following expression, which is in fact very much usable on the GPU. It should be noted, however, that this is only experimental and is not optimal because there are currently no verified IVP solvers on the GPU. And yes, this is only for testing and comparison purposes. So, and then we thought, well, Sivia is the interval algorithm that's very, very well known. So why not use Sivia and try to parallelize that? And so taking this classic example here on the left, we see a generic Sivia implementation. And if we apply Sivia to this, search space at a maximum box width of 0.05, we get a very familiar picture of the solution set to this problem, to this set inversion problem. And we thought, well, why not take this part and parallelize it? So we arrived at this implementation. So this for all step here is executed in parallel on all available cores on the GPU. And we took the bisection, which in classic Sivia happens in this step, and put it at the beginning of our algorithm, and then applied this filtering step to all of those boxes. And from the picture, we can assume that the results are pretty much similar. And so this is the experimental setup and the methods we used. And then we put them to the test for the initial search space of, well, shown above here, at a width of 0.05. And so these are our results. So the first 4 results are for the C or C++ implementations, where the lower 2 are the Julia versions. I have to say the execution times for our little programs here are, for Julia, they include the compile time, which I will explain shortly. And we can see in all cases the resulting enclosure of suitable boxes has been reduced compared to the initial search space. And as expected, the hard-coded version of the exact solution is the fastest. And as soon as we introduce automatic differentiation to this problem, well, the execution time increases dramatically. But this might be due to the fact that we just took a CPU optimized library like FATBAT and put it on the GPU, which does a lot of memory allocations, which are expensive on the GPU again. Also interesting from my view is that the Sivia approach, which is method number 4, yields almost the same results as the approach with the automatic differentiation of the exact solution. So, but there are some performance considerations to be made. So the green lines are the kernel execution times per box, maximum box width for CUDA implementations with and without automatic differentiation. And the purple lines are the Julia implementations. And we can see that Julia is in fact faster by a lot compared to its native language for CUDA, C and C++. But the compile times of Julia implementations are much, much larger as compared to classical C or C++. So this is the point where one has to ask which is more important, the faster execution time, or do we want to wait almost a minute or even many minutes for a kernel just to compile? So what's next from here on? Well, I think we should explore the so-called dynamic parallelism, which is a concept introduced by CUDA some time ago, which allows us to not, well, what we did here is bisect everything in our search space on the CPU and then transfer it to the GPU, which is extremely costly. We don't want to do that to save some time. So dynamic parallelism allows us to generate smaller boxes or larger, a higher resolution of the search space on the GPU directly by invoking kernels from a kernel. And it would be also interesting to see a comparison between the performance of a GPU compared to a low-cost CPU cluster in terms of performance, and also in terms of energy use, not only compared to a low-cost CPU cluster, but also compared to a traditional high-performance CPU cluster. And we also found that where there's still a lot of work to do on the GPU concerning intervals, where the Julia implementations are very flexible, and I think it's a great approach. But if we want to use intervals or in C++ or C on the GPU, we still need a truly platform-independent and complete and well-tested library. And there's also still the need for a GPU compatible ODE solvers. And yes, so with that, I'm open for questions, and thank you very much for your attention.
So many thanks, Lorenz, for your presentation. And as you just mentioned, the talk is now open for discussion. Okay, let's see, Luc.
Yes, maybe. Thank you for the talk. I have a small question. I would like to know where in your CV algorithm, when you perform the computation with many boxes, why they are so small? How many cores you have in parallel? For this one, yes.
Yes.
How many cores you have in parallel here, for instance?
Let me see. It was the device I used this method on had 4,608 cores, and well, again, it's these cores are split into groups, which are then executed in sequence.
Okay, and why it's in the previous slide? Yes, you have a big box, and now you have small box. It's not possible to do some kind of to be between both. So I don't know. To me, it seems that you make a lot of computation, whereas you
Yes.
can be some kind of mixture, taking big boxes, and of course you bisect more due to the fact that you do many computation in parallel. But it seems that it's a brute force approach you apply in the next slide, no?
Yes, absolutely. This is a brute force approach, and this is why I said it is necessary to explore dynamic parallelism, because if we could, Civia works very efficiently on single core and maybe many core systems. But if we could use this Civia approach and apply it on the GPU, where we have, where we could bisect from 1 to 2 to 4 and so on, and do this up until the entire GPU is used, it might be much more efficient and faster than on the CPU. While yes, this is computationally very expensive. You're right.
Okay, thank you. And I have
Maybe
another question.
Just one comment about that. So you cannot see this in the same way as computations on the CPU, because yes, of course, it's computationally expensive if you would carry this out sequentially, but it is not like it is done on the GPU. Yeah, so on the GPU you have many cores, and those cores are executed well, at the same time, let's say, yes. So that's why it's a brute force approach, yes, but it's not so very, not as important as on the GPU, not to have it, you know.
Yeah.
On the GPU, you can allow you, yes, to just yourself to do this, yes, because you just have the computing power.
Oh. Okay, that's clear. And I have another question. So on this example, you don't need automatic differentiation, I think, yes?
This is right, yes.
Okay.
In this Civia-like approach, we did not use automatic differentiation, but in this approach, when computing the gradient, we definitely need automatic differentiation.
But even on the other example, it would be if you use a centered form, for instance, you need the derivative to be.
Yes.
But okay, I understand that. Yes, it's that here you need for the gradient. And
yes, and
But it takes time for this example, probably, no? Yes, yeah, I remember. It takes time to get the minimum. Yes. Because the conditioning is not very good, probably, in this example.
Yes, that's right.
Okay, thank you.
So, do we have any other questions? Marek, do you have a question? No, doesn't seem to be the case. Now, maybe let me ask a question. What you mentioned as an option for doing some high-level programming that was using Julia and interfacing Julia with CUDA, or using the Julia functionalities in order to use CUDA. There exists also the option to use MATLAB in combination with CUDA. You could also define the kernel functions in MATLAB and compile the corresponding kernel functions as CUDA code and employ them. Did you make such kind of comparison?
I tried. I tried doing that, but the CUDA interface for MATLAB only allows standard data types at the moment, and it didn't let me transfer interval arrays to the GPU, which, well.
Okay, then it is still the same problem that I experienced, I think, 4 or 5 years ago when I tried to do exactly the same.
Yes.
And yes, I also didn't manage to resolve it.
It's the same problem in pretty much every higher level language, also Python, which allows GPU computations and has interval libraries. But as soon as you try to combine those two, it doesn't work, which is why Julia is very unique in that regard. And yes, I can only recommend it.
Yes, and maybe concerning again those two different types of problems that you have. There exists, I think, a small but, in my opinion, significant difference between both objective functions that you take into account. This objective function here for the dynamic system model that is getting more and more complicated when time is evolving, just due to the fact that you're recursively substituting in the solution of the ODE, in this case, in the form of a temporally discretized form by using the Euler method. The other example that you had is really just an algebraic function that you're evaluating, and this doesn't have any nested some recursive function evaluations. Can you give us a little bit of an impression of feeling whether this nested evaluations for dynamic system models makes the GPU more efficient or less efficient when just dealing with a single parameter box?
That's a good question. Well, from our results, we can see that the approach using the numerical approximation is actually faster than doing computations with the large algebraic equation expression, excuse me. But yes, this is something I would like to investigate as well. But again, there aren't very many options for ODE solvers available, which is quite sad. But who knows?
Yes, the reason why I'm asking this is what you could have in mind as soon as you have elaborated further on this dynamic scheme that you mentioned in the Outlook. It could also be an option to integrate the ODE over different time horizons. For example, to use a short time horizon already to reduce the search space a bit. And then, for example, to perform further computations for longer times in order to exclude further parameter domains. Because the thing that I'm having in mind is that some of the parameters may be influenced significantly at transient behavior, other parameters have more influence on the steady state behavior. And in such a way, also such kind of consideration of different time horizons would make sense in order to speed up the identification.
Sure, that sounds very reasonable, but again, the tools are just not there yet to try it out.
Okay, any other questions? If this look.
Yes, maybe I understand the importance of parallelism here, and I would like to know if so I don't know if you heard know things about interval constraints propagation, but I think the contraction of the interval could be done maybe in parallel, but maybe it's not as easy as it is for the examples you give here. So have you heard about constraints propagation, and do you think that the GPU and it can be easily be parallelized in a GPU?
I don't know yet, but that's using contractors on the GPU is definitely something I want to try out in the future.
Yeah.
Because I think it should be definitely possible to run a group of contractors in parallel.
Yeah.
Or yeah,
but
maybe also a large amount of contractors in parallel, yes.
Yes, but in some way, the contractors have to communicate between, to collaborate in order to contract. So maybe it's not as easy as it is.
No, it might not be as easy as on the CPU, but it is definitely possible.
Okay.
It is possible for different kernels on the GPU to have inter-process communication.
So okay, good. Thank you.
Okay, and then as soon as you have mentioned to evaluate different contractors weeks ago, then you could do the union of contractors.
Yeah.
Yes, possibly.
Okay, do we have any other question? If not, then again, many thanks, Lorenz, for your presentation, for answering the question. And we'll have our next seminar already Friday next week. And next week, it will be Michelle Kiefer who will give a talk in our online seminar.
Well,
and
thank you
see
for
you all
inviting me.
soon. Have a nice Friday afternoon. Have a nice weekend and see you next week.
Yeah. Thank you. Bye.